This is the 2009 Taylor Series 1. Looks like it involves manipulating e to the x. So here's the problem. It does tell us that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Right? It tells us what we know for e. It defines f as this exponential minus 1 over something. We've done questions like that before. It tells us that f of 1 is 1, which is the original y value. Right? This is some function centered at 1. Okay, so first thing, write the first four non-zero terms in the general term for this series. Use this series to then actually find out what f is, because f is going to involve this guy. C is going to say use the ratio test. Doesn't really have to tell us that. It could just say find the interval of convergence, and we should know to use the ratio test. And then part D says use this Taylor series to show whether or not f has any points of inflection. So it's kind of going back to some Calc AB stuff of what it means to have a point of inflection. Okay, so let's start with this first part. And they do give us this. It's an unnecessary piece. We should know this, that e is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 x to the n over n factorial. So that's what e is. And then part A says, write the first four non-zero terms and the general term for the function e to the x minus 1 squared. It's really just a substitution problem. It's kind of a weird one, but you're just going to put x minus 1 squared in for all these x's. So 1 plus x minus 1 squared in for x plus x minus 1 squared, so that's to the fourth, over 2 factorial, plus x minus 1 squared cubed, which is to the sixth, over 3 factorial, plus dot dot dot, x minus 1 squared to the n, so x minus 1 to the 2n, over n factorial. Okay, so that's just, they gave us this and we're just making a substitution. And I said the first four non-zero terms, 1, 2, 3, 4, dot dot dot, and then the general term. Okay, that sound good to everybody? Okay, part B, use this Taylor series and actually do what f is. So we've done questions like this before where they define f as e to the x minus 1 squared minus 1 all over x minus 1 squared. Okay, so what is that? Well, it's this kind of silly shifting thing because we're going to take this whole polynomial, which is e to the x minus 1 squared, and if we take away 1, well, all that does, if you take this thing, minus 1, all it does is get rid of this. And then if we divide all the remaining terms by x minus 1 squared, it'll make this equal to 1. It'll make this x minus 1 squared over 2 factorial. It'll make this plus x minus 1 to the fourth over 3 factorial plus dot dot dot. It'll make this one x minus 1 to the 2n minus 2 over n factorial. Okay, it took away the 1, it made that a 1, and then it just decreases all of those by 2 factors of this, which is just taking away 2, minus 2, minus 2, minus 2, minus 2. And then we have this, which is b. And again, you could have b, you could have this be a little bit different if you wanted to shift these around a little bit, but you know what we have here is pretty solid. Okay, so part C says use the ratio test. The ratio test is looking at the limit of a to the n plus 1 over a to the n as n goes to infinity. Okay, and then again, looking at the general term here, we're going to shift this up by an n value of 1, but shifting that up to n plus 1 minus 2 over n plus plus 1 factorial all over x minus 1 to 2n minus 2 over n factorial. Okay, this is 2n plus 2 minus 2, so that's really just 2n, and this is 2n minus 2, so it's 2 less factors of it down here. So there's 2 more up here, so that's an x minus 1 squared left over, and then just think about n plus 1 factorial, and this n factorial is in the numerator, right? If you rip off an n plus 1, that's really just n factorial times n plus 1 times n factorial, and those cancel, so we're left with n plus 1. And then, but we're looking at the limit as n goes to infinity, so that's equal to 0 for all x. And so the interval of convergence is all reals. And remember, if you think about the function, the factorial will dominate the exponential. And so no matter what you make x can be whatever you want it to be, the factorial will always make this series converge. Okay, so we found the radius. And then on part D, it says, is there any points of inflection for f? Okay, now let's look at f here. Okay, what do we notice about f? Well, it's got a function value of 1, but what's the first derivative? Well, the function's value is 1. The derivative at 1 has to be 0, and there's no other term. The second derivative is positive, because this is a positive number here, right? It's actually just 1, it's that coefficient. And here's what you want to realize. All of these are just plus, 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 and they're all even powers. Okay? So for there to be a point of inflection, well, we'd have to have a change in concavity. So we'd have to figure out where is the second derivative equaling to 0, and we'd have to have it like be a plus and then a minus. Okay? So in this case, the second derivative is positive for all x, because how would it ever be negative? All of these terms here are positive. All their derivatives will be positive, and you'll never get a change of inflection because it's a squared, a fourth, a sixth, an eighth, a tenth. Right? We can never have a sign change. Okay? Everyone okay with that? Again, if you want to, go ahead and take 2 derivatives of all of these terms. This square will go to a constant, the fourth will go to a square, the sixth will go to a fourth, the eighth term will go to a sixth, and the second derivative will still be a collection of all even powers, of which there'll be no sign change, and so the second derivative will always be greater than 0, so there's no point of inflection for anything. Okay, the key says something like this. You're looking at the actual key. Right, this is what it says. It actually takes the second derivative and shows that the second derivative is positive, and then a collection of plus. All these are positives, and they're squares and fourths and sixths. Since every term in the series is non-negative, the derivative is always positive. Therefore, the graph has no points of inflections. Hopefully that's something similar to what I said. Okay, so if we look at 2009, it starts us out with E. It has a substitute into E. It adapts it by subtracting 1 and decreasing the power to form some new series for f. It looks at the interval of convergence for f, and ends up being that it's all because of the factorial. And then it asks us some calc AB concept like previous problems have asked us for maxes and mins, and this one happened to ask for points of inflection. Go back to the definition of a point of inflection. It's a changing of the sign of the second derivative. But in this case, the second derivative is positive, and all the other successive terms are positive, so there can be no sign change. Okay, that was 2009.